Hi, my name is Shoykot Basu. I'm an assistant professor of mechanical engineering at South Dakota State University. Thanks for the invitation, and I apologize for missing this conference in person. Today, I'm going to discuss our work on particle filters that have been inspired from animal noses. The project is a collaboration with Leonardo Chamorro at UIUC and Sunny Chang at Cornell University. We launched this project during the COVID-19 pandemic to come up with new designs for filters in a face mask, a filter that can screen the aerosols and droplets that are primarily responsible in carrying the infection-causing viral load into one's airway. We also wanted the design to be more breathable than the masks available commercially. The concept is based on the airway shape found in high olfactory mammals, such as pigs and dogs. The nasal passage is much more complex than the human nose. As a result, the inhaled airflow develops recirculation patterns with vortex formations that have a low pressure at their centers. These flow structures can slow down and even trap particles embedded in the inhaled air. And if these particles are odorants, then that process also elevates the animal's sense of smell. We looked at the CT-based images of a number of animal airways, as you can see on this slide, and we quantified the geometric complexity of the nasal passage in terms of a quantity called tortuosity. Tortuosity is defined as the ratio of the curved distance between 2 points along the surface of the airway walls to the linear spatial distance. So more complex is the airflow corridor, higher would be the tortuosity value. Let's now look at a typical example of a filter channel design. This channel on the right has a tortuosity value of 1.9, which is similar to that of pig airway. On the left is the resulting filter bed, which is a collection of these channel pathways. In this particular example, the bed comprised around 300 filter channels. So essentially, we are trying to replicate the tortuosity, which is a marker of the geometric complexity of the animal nasal passage, in our bio-inspired filter design. We have tested our designs both numerically and experimentally. On the left is the experimental setup in a small wind tunnel. On the right is the numerical in silico setup. In both cases, we replicated airflow that are similar to human breathing rates, so within the approximate range of 15 to 85 liters per minute. These are the results for the pressure drop to drive the airflow across the filter channels. This was a validation of our numerical simulations, which used LES schemes. Despite some minor differences, the trend of the pressure versus the airflow velocity curves, both obtained numerically and experimentally, they agreed. We also ran experiments with surgical masks and N95 filters. For both, the pressure drop needed to drive the flow across was higher than the bio-inspired filters. And these are the curves at the very top over here. In this plot, we further examined the pressure loss comparison. The 3 data points on the top right are for surgical masks, N95s, and HEPA filters. Their higher pressure loss signifies that it is relatively harder to breathe or pass air through them than the bio-inspired filters. In other words, bio-inspiration would make a filter more breathable if it is used in a face mask and more energy efficient for other large-scale installations. Now, of course, N95s will still be more efficient in screening submicron particles if we think of a face mask. However, from our research published in 2021, which has since been validated through studies by other independent groups, we have seen that infectious dose for at least COVID-19 is primarily carried by droplets and aerosols that are sized between 2 and 20 microns. In fact, 85% of the infection triggering load is found to be embedded in particles that are bigger than 9 microns. And these results are obtained in context of which droplets and aerosols are more effective at reaching the nasopharynx, which is the initial infection hotspot for respiratory viruses. The nasopharynx is marked in red in the visual on the right. So in case of our concept filters, we see that the capturing efficiency for such droplet and aerosol sizes is very close to 100%. Therefore, while the filters are not as efficient as N95s for the smaller particles, they can still be trusted to carry out a targeted screening of the hazardous particle sizes with less energy expended to draw the air through the airflow passage. These are some sample simulations to show the complex airflow patterns formed in the bio-inspired filter channels. And these visuals show the particle capturing trends for the typical particle size of 3.5 microns, which lies within the hazardous particle size range for infection onset for respiratory viruses. We have tested our concept for a wide range of tortuosity values, as you saw in the plots from the previous slides. This is what the corresponding channels would look like. I would again like to point out the recirculating regions in the airflow field, as can be seen in the visual on the right. These are the flow structures that are modulating the screening process. There is another phenomenon that we have come across. When air passes through the animal nasal passage, it warms up rapidly. This thermal conditioning effect is controlled by the flow physics and can be an important feature toward designing real-life applications. At this point, I think we can translate this concept beyond face masks for more large-scale installations. For example, we can think of filter baffles that can be placed over ventilation ducts inside closed spaces like a car or an aircraft cabin. The mask project was funded by the US National Science Foundation, and I'm open to new collaborations to explore the future directions. If you are interested to discuss on this topic or if you have any follow-up questions, please feel free to send me an email. My email address is at the bottom right. Again, apologies for not being there in person, and thank you for inviting me. Hope you have a great conference in Berlin.